Welcome back to Arxflix. Today, we're diving into an intriguing new paper titled Linear Transformers with Learnable Kernel Functions Are Better in Context Models. This paper is a step forward in advancing subquadratic architectures for language models, LMs, by enhancing in-context learning capabilities. Here's a snapshot of the rebased model's performance, demonstrating its superiority over other baseline models in handling multiple sequence lengths. Let's break down the main points of this paper. Traditional transformers have revolutionized NLP, but struggle with scaling as sequence lengths increase due to their quadratic complexity in attention mechanisms. This becomes computationally intensive and impractical for long texts. To address this, Katharopoulos et al. Proposed using kernel functions in attention mechanisms, reducing complexity from quadratic to linear. This modification trades off some performance when compared to the conventional transformer models. The above equation represents how the similarity between queries and keys is approximated using kernel functions, transforming the computational process. The based model introduced a novel hybrid architecture, utilizing a kernel function derived from Taylor series expansions combined with convolutional networks, showing enhanced performance on tasks requiring longer context management, like the multi-query associative recall (MQR) task. This figure shows how the kernel functions could be refined. The based model's similarity scores have a minimum value of 0.5, making it difficult to ignore irrelevant tokens entirely. To improve this, the authors propose a new kernel approach, allowing the similarity to drop to 0, enhancing the model's precision on long sequences. Enter rebased. This model refines the based architecture by adjusting the kernel function to better handle long content, introducing normalization and learnable kernel parameters to achieve closer alignment with ideal attention distribution. This modified kernel incorporates an affine transformation and normalization, making the attention mechanism more adaptable and precise. The authors conducted thorough experiments to validate rebased's efficacy. On the MQR task, rebase consistently outperformed other subquadratic models and even matched traditional attention mechanisms in longer sequences. This figure illustrates the ablative study showing rebased strong performance across sequence lengths of 256 and 2048, highlighting its stability and efficiency. For language modeling tasks, rebase was trained using the PILE dataset, where it showed better perplexity metrics compared to the based and traditional transformer models, showcasing an improved capability in modeling associative dependencies. Figure 5 gives us a look into attention matrices across different models. The intersection over union (IOU) scores reveal rebased's ability to closely approximate attention mechanisms, essential for effective token retrieval. The rebased model presents a meaningful leap in subquadratic attention computation, integrating learnable kernels and normalization to enhance in-context learning and long sequence processing. The authors suggest further exploration into more sophisticated kernels to bridge the gap with traditional attention mechanisms even more. This wraps up our overview of linear transformers with learnable kernel functions are better in context models. Thanks for watching, and make sure to subscribe for more insights into cutting-edge research. Thanks a lot to Element for supporting Arxflix and providing this wonderful voice.